Okay, welcome to the participant talks. We will use the same process as last time. You get 4 minutes for the talk, and there will be a 1 minute warning, namely 3 minutes into your talk, and then the bell at 4 minutes. Then I'll ask for at most one question. When you stand here, please talk into this microphone so that we don't need to pass things, and you use this pointer that's here. Okay. So the first speaker is Confinement from NYU. We'll see the title.
Okay, thank you. This talk is based on the work with Andrew, Sergey, and Mike, which hopefully will be published in the summer. The motivation for our works is that there has been new Monte Carlo data that provide confining string spectrum with higher excited states and also higher precision. So we've tried to see that if the low-lying spectrum can be described in the framework of effective string theory with the well-shaped axion. And we also try to incorporate the leading order interactions involving axions in terms of TT-bar deformation. So effective string theory is described by D-2 Goldstone bosons, which comes from the spontaneity breaking of the space-time Poincare symmetry. And if you write down the most general effective action that is allowed by the symmetry, we see that there's a low energy universality, and the leading term is given by number equal to action. And well, this action is valid up to the scale of the bulk gap or massive resonance on the wall sheet. So when we reach that end scale, we need modification. In 4D Young-Mills theory, the Monte Carlo results indicate that there is a massive resonance at low energy, which shall be described by this Lagrangian of the massive pseudo-scalar coupled to a topological invariant. And this is the plot that Sergey has already shown you this morning, but this is like with the new data and higher precision, and we see that with including the axion, we get a much better match in terms of the previous number go-to prediction. And okay, I think there's so there's a systematic way of going from the effective action to the final volume spectrum, which is called the thermodynamic path ansatz. And we start from the effective action and compute in perturbation theory the scattering amplitude of the two Goldstone bosons. And here is the results in the low energy, and well, with the resonance, we kind of need this extra part. And then the leading integrable phase shift of the Goldstone boson can be obtained from TT-bar deformation. So if we ignore the higher order terms in the winding corrections, we can simplify the procedures into asymptotic path ansatz with TT-bar deformation. And we also assume that the leading interaction involving axions can be described by the TT-bar deformation. So here are a few examples. This is the example of the state with one Goldstone boson and one axion, denoted in the red dots. And we see that the theoretical prediction is pretty well. And the black dots are the previous states from the effective action without an axion. So this is like an actual state when we include the massive axion. And this is the example of two axions. And we see that the blue dashed line is two axions without interaction at all. And the blue solid line is the two axions with the interactions coming from TT-bar deformation. And we see that when we include the interaction, it has much better fit to the Monte Carlo data. And this is the example that Sergey has mentioned today, like in the 0± sector. We have these high excited states. When we include high order corrections, we get a better fit towards the phase shift. So the conclusion is that all the low-lying confining string spectrum in 4D Young-Mills that we have observed can be described in the framework of the effective string action and with a massive axion. And also the interaction involving axions can be described by the TT-bar deformation. Okay, that's it. Thank you.
Thank you. Question?
explain more deeply this last model definition?
This one? Yes. I mean, so this is the first excited state in this sector, and that dashed line is the prediction from the DVA without the high order corrections, and we see that it's much worse fit to the Monte Carlo data. So now we've included up to S to the 4 terms, so which means there are 2 more parameters, and into the fitting and do that data information again, we see that it kind of has better fit. And this can be also seen in this phase shift. So we kind of see that this becomes flat in the middle, and then at higher energies, the data show the trend to go up. So which kind of, well, indicates that we cannot use the simplest version of that low energy effective action.
Points here, like the
Sorry, which one?
It's a group of points with 1.
This one?
Here?
Yes. This comes from the stage here. This is because in the Monte Carlo simulations, when we increase the string length, well, because the energy grows linearly, which means that the total energy is larger. Here I actually deduct the linear growing part, but a large mass in the Monte Carlo actually means that it will have larger systematic error, and it will kind of, so the correlators is exponentially suppressed. And we want to extract the exponent of the exponential behavior. So it will kind of disappear into the noise faster, which leads to this larger error bars, and also this systematic overestimation of the mass spectrum. This is very typical in the confined spectrum from Monte Carlo data.
All right, thanks a lot. Yeah.
Thank you.
We move on to the Andrea Luzio from Scuola Normale.
Everybody, today I'm gonna talk about chiral gauge theories, anomalies, and vortices. I'm gonna focus on the Psieta model, which is SUSY mills plus a chiral matter content in 4 dimensions, and the theory is strongly coupled in the IR, and so we are interested in what happens in the far infrared. In particular, how the system realizes its global symmetries. Surprisingly, there is a very simple baryon that reproduces all the perturbative Toft anomalies. So confinement without symmetry breaking seems to be allowed by this a phase with only this baryon. However, if you look more carefully at the global structure of the internal symmetry group, there is a non-trivial denominator. So you can consider a background with fractional color favor locked fluxes parameterized by this quantity BC. And in particular, if you allow your space-time manifold to have fermion parity defects, which are codimensional 2 surfaces around which you have a non-trivial fermion parity holonomy, then BC can be said to be odd. And the fermion parity itself, it's anomalous in the Psieta model, but non-anomalous in a phase with only the baryon. So there is an anomaly mismatch, and it seems that we should be putting a trash can in this phase. But should we allow for these defects, or is there any subtlety? Well, to understand this issue, we decided to define more physically what we mean by these defects by abandoning the Psieta model in X-ray theory, where the fermion parity is embedded in a continuous U1 symmetry, broken at an energy scale by a scalar web. If you do this in the standard background or in this even in general, you get back the Psieta model plus a decoupled Navier-Stokes boson. But if you do this in a BC odd case, then what you get also vortices and chiral 2D fermions stuck on the vortices. And these vortices are the physical realization of these defects, and they doesn't really change the fact that the system has a fermion parity anomaly. So a phase with only a bulk baryon does not reproduce this anomaly. Can we still realize somehow a confining phase? Yeah, we have simply to modify a little bit something. We started by this X-ray theory, which has this fermion parity anomaly, this -1, seeing it. And if you set the scalar web to be big, you flow to the Psieta model, which carries this anomaly, plus fermion on the vortices that doesn't carry this, doesn't modify this anomaly. But all the anomalies of the X-ray theory are matched by a phase with the original baryon, plus also other 4 baryons. And if you set directly the scalar web to be directly in this effective theory, then you flow in a theory where in the bulk you have the original baryon, but on the vortices you have other fermions, and they carry a fermion parity anomaly. So in this phase is totally fine for anomalies, and it's very natural if there is no phase transition between a small scalar web and a big scalar web. However, it's possible only if there is if the fermion on the vortices here doesn't decouple by the bulk. Otherwise, you should match the bulk with the bulk and the vortex with the vortex. Thanks.
Any questions? If not, let's move on. Antonina Mai from City University of New York Graduate Center.
So it moves, yes. Okay. All right. So I'm going to talk about 4D non-abelian gauge theories that live on a complex projective space of dimension 2. It's work that I've done with my supervisors, Dimitra Karabali and Parameshwaran Nair, and it's a kind of natural extension of the stuff they've done in 2 and 2+1 gauge theories that you've seen last week. The main motivation is the kind of holy grail of getting an analytical understanding of non-perturbative QCD, and we do that by considering a Yang-Mills theory on a complex 2D space rather than 4D real space. In particular, on CP2, you can, similarly as in the 2D case, find a parametrization of your gauge fields on which the gauge transformations act homogeneously, and that allows you to get rid of the measure for the gauge modes in a kind of global and manifestly gauge invariant way. So the first question is why CP2? So you saw that in the 2D case, there was no mention of CP1, so what's the difference? So in 4D Euclidean space has no unique complex structure, unlike 2D Euclidean space. So there are many ways in which you can assemble 4 real numbers into 2 complex ones. So we have to choose a 2D complex manifold, and we choose CP2. So the main advantage is that it has this group theory structure as SU free mod U2. That kind of means that you can use group theory tools to find the most general parametrization of your gauge fields, like they did in 2D. And secondly, it's a finite space with a kind of easy flat space limit. So it's very easy to recover flat 2D complex space from CP2. So now let's say that we use these group theory tools. So the most general parametrization you find is this. So it's very similar to the 2D case, but with these extra terms. And like in the 2D case, the M and M dagger fields belong to the complexification of the gauge group. And in particular, as in the 2D case, you can rewrite them in terms of these gauge invariant modes and the pure gauge modes that belong to the gauge subgroup. And these little A and A bar fields can be seen as kind of transverse modes of the gauge fields, and they're gauge invariant. So it's kind of clear that your gauge degrees of freedom are now given by the U modes, and your gauge invariant degrees of freedom are given by the H fields and the little A and A bars. So as before, we have a kind of new coordinates for our gauge fields. And now you find the measure for the gauge fields in terms of these new coordinates, and you just factorize out the volume measure for the pure gauge modes. And what you end up having from these new coordinates is a Jacobian. and that is now manifestly gauge invariant, like you saw a week ago. And I don't have much time to get into kind of the details of this measure, but it's the main thing to say, it's much more complicated in the 4D case than in the 2D case. It's highly non-local, it has infinitely many terms, but we argue that there is a low energy kind of regime where you can approximate it as the 4D Wezumino-Witten action for the H modes. So to bring it into kind of analogy to the 2D case. And why is this important in terms of confinement? Well, you saw last week that in the 2+1 theory, you get this Wezumino-Witten action in the measure, and you can calculate the expectation value of the Wilson loop directly there, and you get an area law behavior. And the question is, can we do kind of something analogous for the 4D case? And the honest answer is, well, it's much more complicated. The calculations are much more complicated in the 4D case. What you can show, and maybe it's not much, is that in the absence of this Yang-Mills action, in the 2D case as in the 4D case, you get this UV divergence, but we can't show that the presence of the F-squared term regularizes it like we expect for confinement. All right, thank you.
Question. So can you tell if there is going to be Casimir scaling again, or is it too hard?
So that's actually the next thing we're looking at, because there have been some kind of lattice calculations that came out this year about Casimir energy. So we expect that a similar sort of mechanism will happen, and we can find it. Yeah.
Okay.
All right.
Thank you.
Thank you.
The next speaker is Colin Nancarrow from Boston University.
Hello. Yeah, my name's Colin. This is work that I did with Yuan Xin called the Spectral Bootstrap. This is a bootstrap method for arbitrary Hamiltonian systems. So in our method, our consistency condition is this crossing equation on the left. So this is familiar from quantum mechanics. You just insert the identity in between two operators. But since we don't have conformal symmetry all the time, we want to affect a kind of block expansion that uses a different fundamental idea. So here we've got the Hamiltonian equations of motion on the right. Now, when you plug in a particular Hamiltonian, these equations will induce relationships between matrix elements mediated by factors of the energy. This allows you to express an arbitrary matrix element as a sum over just a small primary set of matrix elements. And those factors, the G's right there, will be known functions of the energy. So to turn this into a bootstrap problem, what we have to do is write down the crossing equation for some particular pair of operators, and then plug the block expansion into each of the factors that appear. With this sort of procedure on the right, it's easy to see that you can put this into a quadratic form. So you expand both of those factors, and you get these vectors C, which are 3×1 vectors containing those blue matrix elements in the block expansion. And then you also get these conformal blocks, script V, which are 3×3 matrices of these known functions that you'd obtained by reducing the equations of motion. Then you loop through as many different operators in your theory as you can, so that x to the I plus j, you do this for all the different i's and j's, and you get a big list of these crossing equations, which we indicate with a vector hat. So the numerical problem then becomes familiar to bootstrappers. We have a crossing equation in this form, and we seek a linear combination alpha that's going to somehow rule out a particular spectrum. So the very particular numerical procedures, if there exists an alpha such that its action on these blocks creates a positive semi-definite matrix for all energies above some prescribed gap, and also the action on the vacuum channel is a positive semi-definite as well, then all the spectra with that prescribed gap are going to be ruled out. And this is a problem for which there are well-developed numerical methods. So here is the result that we get for plugging in a particular Hamiltonian, the quartic anharmonic oscillator. we take operators up to x to the 8, and we get these sorts of bounds on the spectrum and the matrix elements. So these are sharp bounds. These are not statistical errors. These are bounded from above and below. And on the right, we've got one of these classic conformal bootstrap island plots where this is our allowed region. And you can see on the x and y axes that those are pretty small numbers. So this is not the only matrix bootstrap. There's another very good one that does not use the off-diagonal matrix elements, but you have to go to much higher degrees in the operators. So when you go to x to the 14, then you get that kind of precision down there, which is really only in the first digit. So in my opinion, the main virtue of this method is that if you're a conformal bootstrapper, you get to reuse a lot of what you've learned for the conformal bootstrap. There's a very, very sharp dictionary, and you can use all of the same numerics that you're familiar with, like extremal functional method, navigator, skydiving. And then finally, just to prove that it's not only for single body systems, we also did it for the transverse field Ising model in 1+1 dimensions. And this is a result in the thermodynamic limit. So you can't use one of these two equations, but you can still get a lot done. And here's a plot of the gap as a function of the transverse field. The final thing that we'd like to investigate is, could we possibly lower bound the gap instead of upper bounding it? Thank you.
So questions?
So can you comment on how this scales when you have, so here you showed 1 degree of freedom in quantum mechanics, and then here it was a spin system. So suppose you have many degrees of freedom, like in a matrix quantum mechanics or something like that.
So there are other methods for matrix quantum mechanics that I think scale pretty favorably, in the sense that the size of the matrix n just shows up as a parameter in some of your loop equations, as opposed to actually scaling with the problem at all. Here, one thing I can comment about on the scaling is that we've taken this basis of local spin operators and then generated descendants by acting with the Hamiltonian and translation. And this is in some way the worst naive basis that you could choose for this problem. It gives you actually pretty bad scaling. And the thing that we're working on right now is to use maybe a basis of other kinds of states that will give us better performance.
All right, let's thank Colin again. The next speaker is Patrick Orr from MIT.
Let's see. There we go. Hi, everyone. So today I'm going to be talking about some work that I've been doing with Will J. and Fiala Shanahan to simulate 2D adjoint QCD using lattice gauge theory. This is still a pretty young project. We just started it a couple months ago, so I'm not really going to be presenting many numerical results, but instead I want to walk through the structure of the calculation, the basic thing that we're trying to achieve. So 2D adjoint QCD is a theory with a single Majorana fermion of mass m coupled in the adjoint representation to an SUN gauge field in 2 space-time dimensions with the following Lagrangian here. Now, when the Majorana fermion is massive, this theory confines fundamental Wilson lines, and when it's massless, it actually deconfines. And the reason we're interested in studying adjoint QCD is because there's been a large number of analytic computations of this theory that have computed things like the string tension, the chiral symmetry breaking pattern, and the spectrum of the theory. And all of these things, in particular the low-lying spectrum, because the full spectrum is a lot harder to compute on the lattice, all of these quantities are amenable to a lattice Monte Carlo simulation. So our goal is to numerically try to compute these quantities and then match them to the analytic predictions. So to discretize adjoint QCD, we're going to begin by just using a simple Wilson fermion discretization, basically just as a proof of concept. You can write out the Dirac operator here in terms of the adjoint gauge fields, V mu. And here, this Dirac operator is for a massive Majorana fermion. Now, as you take the mass to 0, this thing becomes more and more singular, so it's much harder to simulate. So we really have to look at the massless, or at the massive case. Of course, Wilson fermions, while they gap out the doublers, they also sort of destroy the chiral symmetry of the system. So this is very much a proof of concept. And once we get things working with Wilson fermions, we plan to move to an overlap action. So overlap actions have exact lattice chiral symmetry, i.e. the Ginzburg-Wilson relation, but they're a lot more computationally demanding to compute. And this is sort of the crux of why I think you haven't seen a 2D adjoint QCD computation using lattice gauge theory before, is because Majorana fermions are pretty hard to simulate on the lattice. So generally, we're trying to compute k-point correlation functions by sampling from a probability distribution to compute the path integral. And when your fermions are Dirac, what you get is you can integrate the fermions out and you get a determinant of the Dirac operator. Now, in many cases, you can show this is a real and positive density, which means that you could sample it using a Markov chain. The reason why Majorana fermions are hard is because instead of getting a fermion determinant, you get a fermion Pfaffian, so the square root of the determinant. And the issue is that this Pfaffian is real, but it's not necessarily positive. Now, when it's negative, you can have major issues like a sign problem because you can't treat this like a probability density if that's negative. So luckily, there's a way to get around this called reweighting. And the idea is to basically take the sign of the Pfaffian and absorb it into the operators that you're looking at, and then use the norm of the Pfaffian, which is now a positive quantity, and absorb that into your probability measure. So thank you. So you're using now basically this partially quenched, we call it, probability measure, and defining all your correlation functions in terms of that. You can, just like I said before, strip off the sign of the Pfaffian and absorb it into your operator definition and compute it using these partially quenched correlators. But importantly, this will fail if the sign of the Pfaffian is 0. So you have to measure the sign of the Pfaffian of the Dirac operator throughout the computation to make sure that you still are doing things okay. And the sign vanishes, you have major issues, and it's very hard to simulate the theory. So we wanted to get an idea of what the Pfaffian looked like before doing before really starting the computation. So we randomly sampled 10,000 SE2 gauge field configurations on a 4x4 lattice because I'm still running things on my computer before we move it or upgrade it to larger systems. And we computed the Pfaffian of the Dirac operator for this discretization on each of these configurations. And this is the distribution you get. So in particular, it's peaked around 1, and the minimum value is 0.76. So it never goes negative, which would indicate that there's probably not a need to reweight. This is not an exhaustive proof because there still could be negative configurations. And we're also not even sampling from the partially quenched distribution. But ideally, this would show us that our next step can be to actually generate gauge field configurations and start computing things. So thank you.
Questions?
Yeah.
Oh, there was someone.
This reweighting technique, how general is it? Is it only for Majorana fermions or 2 dimensions?
Good question. You can do it for other actions that have a sign problem. So basically, as long as you can sort of strip off an imaginary part of the action, you can absorb that into your observable definition. And the issue is when you have things that are purely imaginary or have really, really bad sign problems, like if you're trying to simulate something like only a chemical potential, and then you might have issues where things like this become 0. Yeah, it also will depend on your discretization because there are certain discretizations that might make this thing specifically 0, or it might make it very small so that you need way too many statistics to really compute anything.
All right. Let's thank Patrick again. Next speaker is Edwin Priot. Did I pronounce it? Yeah. From APC Paris.
All right, thank you. So I'm going to be talking about neutrino transport in holography. I'm going to start with some motivation. So the idea is that neutrino radiation is the main mechanism for neutron star cooling. And to understand it requires to compute the retarded 2-point function for chiral currents in the neutron star matter. But this is a strongly coupled quantity, so you need a non-perturbative method. And in this work, we applied for the first time the holographic approach to this problem. And as a first step, we considered a holographic setup, which is the simplest bottom-up toy model with chiral currents, whereas the bottom-up nature of the model means that we start from a 5-dimensional Borg theory and then use the holographic dictionary that tells us that the stress tensor and chiral current should be dual to the metric and a chiral gauge field. And the action that describes dynamics of those Borg fields is a very simple quadratic action with a Einstein-Hilbert for the color sector and Young-Mills for the flavor sector. And as usual, we have a large n limit, but here the number of flavors will be of the same order of the number of colors, such that in this limit, there is a finite back reaction of the flavor sector onto the color sector, which is important to describe high density. All right, so the background solution that we use is describes an equilibrium state at finite temperature and quark chemical potential, which is dual in the bulk to a charged black hole with charge proportional to the chemical potential. And then we want to compute the retarded two-point function for the chiral currents in this equilibrium state. And the way it is done in holography is by solving the linearized equations of motion for the perturbations of the gauge field in the bulk with infalling boundary conditions at the horizon. And then the solution of these equations will contain the information of this two-point function. So even for such a simple system as a charged black hole, solving these equations has to be done numerically. But okay, so this is what we did, and I will show you some numerical results. But before going there, I will give a very short reminder of the hydrodynamic approximation because it will be useful to understand the numerical results. And this hydrodynamics tells us that equilibrium correlators follow a universal long-range structure, which is given by an expansion in the energy and momentum in units of the temperature, which is a microscopic scale of the theory. But previous results in the charged black hole background have shown that this approximation actually extends to energies and momentum much larger than the temperature, as long as it is much smaller than the chemical potential. And in the context of neutrino transport, this translates into the condition that the leptonic energies are much smaller than the baryonic scale. And in this simple model, we can compute at high density what are those leptonic scales. And we find that they are actually proportional to the baryonic scale, but with coefficients that are quite small compared to 1, suggesting that this hydro approximation may be reasonable. And to check that, we need to go to the numerical results. And here what I show are the so-called opacities, which controls the transport of neutrinos. And I show for neutrinos and antineutrinos. And what I show is actually the relative difference of these opacities with the hydrodynamic approximation in the two-dimensional space with neutrino energy and density. And this plot showed that at low energies, the hydro approximation is quite good and becomes worse and worse with energy. But it remains actually quite good when you go to high density, because the actual criteria is that the energy should be smaller than the chemical potential. Okay, the last result I will show is a comparison of the absolute value of this opacity with the leading order result from perturbative QCD, which shows that our result is about 2 orders of magnitude smaller, which suggests that strong coupling effects highly suppress the neutrino opacity. Thank you.
Questions? Is this strong suppression sort of expected qualitatively?
Well, I would say it could be probably related to the fact that here we have this well, in strongly coupled media, you have this result that the viscosity is much smaller than for a weakly coupled medium. So probably, yeah, I would say that this is related to that. That when the neutrino comes in and propagates in the medium, then there is a less viscosity.
Okay. Thanks. Thank you again. Ajit Kumar from UMass Amherst.
Good evening, everyone. Today I will talk about our upcoming work. It's about deciphering the phases of n equals to 1 supersymmetric SUN gauge theory using quartz CFTs. So focus of our study is two very simple theory, SUN gauge theories. On one hand, we have in which we have a matter in a fundamental, anti-fundamental, and anti-symmetric representation. On another case, we have a matter in a fundamental, anti-fundamental, and symmetric representation. And you can write these Lagrangian in terms of these Coué diagrams also, where you have these flavor symmetries, and in between you have SUN gauge group. Now, if we stay in the asymptotic regime of these theories, as you flow to the IR, these are strongly coupled theories. So as you will change your number of, as you will change N and F, their IR phase structure is very rich, but it's very difficult to understand them. So one of the tools which is often useful in understanding IR is a maximized R symmetry, because using a maximized R symmetry, you can tell what are the dimensions of different operators in the IR, and as you are changing the flavors F. But it has its own limitations. Sometimes some of the operators have negative R charge, which correspond to violation of unitarity. So either it means you have accidental U1 symmetry or some other interesting dynamics is at play in the IR. So for the purpose of understanding the strongly coupled physics better, usually dual descriptions are very useful. And for n equals to 1 supersymmetry, Seiberg duality is actually one of the most powerful tools. So let's try to build some dual description. So if we start for the theory A here is antisymmetric theory, we can't directly build Seiberg dual because Seiberg duality only works when you have a matter in a fundamental, anti-fundamental, or vector representation. So we need a workaround, and we can use something called deconfinement. We can think of this tensor matter here is coming from some confinement of some gauge group here. So we can replace our antisymmetric matter here with these bunch of these chiral fields and different gauge group, and then use subsequent Seiberg duality, and it give us a dual descriptions. You can match, it's a dual description using anomalies, global symmetries, and superconformal index also. Surprisingly, this dual description aligns with a quartz CFT, which has origin in string theory. So quartz CFTs are extracted from brane tiling, which are actually intersection of D5 and NS5 branes and O5 orientifold fixed point. And these are 4 NS5 branes crossing, that's why quad. And if you extract them, there are two kinds of quartz CFTs there. One is called QUSP quartz CFT, other is QSO, and they have different global symmetry group. You can further generalize them by deforming their symmetries. You can break them into subgroups, and these are called flipped CFTs, and they will help us understanding IR phase structure of these theories. So this flipped QUSP theory, if you gauge this group, the Lagrangian that we are getting here is exactly the same Lagrangian what we got after deconfinement and dualizing. So this helps us in understanding the full IR phase structure of our SUN gauge theory with the antisymmetric tensor. Now, can we do the same thing for the symmetric tensor? Answer is no. So say separate slide, I guess. Yeah. So if we do the deconfinement procedure for this theory, symmetric tensor theory, what you get operators with a negative dimension. So it leads to a inconsistent dual description. So you need a consistent dual description, which we can take inspiration from the last case. And we can construct our dual description using the second class of quartz CFTs. These are QSO quartz CFTs, and this is their Lagrangian. So if you gauge one of the global symmetry, and the theory that you get is exactly dual to our UV theory with the symmetric tensor. And this helps us in understanding the full IR phase structure of these theories, where you have a mixed phase for F greater than n-2, and you have a complete quartz CFT for F equals to n-4. So we found a duality, as well as we described their full phase structure of both the theories. Thank you.
Thanks. Any questions? If not, let's thank Ajit again. Martin Rehorst from École Polytechnique Paris.
Thank you. I'll talk about my upcoming work together with Slava Vichkov and Balt van Rees and Benoit Suiva about bootstrapping frustrated magnets. So I'll tell you what I did, why I did it, and how I did it. Specifically, what are frustrated magnets? What is the controversy that we're trying to solve, and how do we solve it using the numerical conformal bootstrap? So we know that second order phase transitions are described by conformal field theories, and specifically many types of magnets. This second order phase transition has been solved, for example, by numerical conformal bootstrap, by determining the critical exponents that describe the physics at these second order phase transitions. But there are also many magnets that show more complicated behavior. Specifically, there are so-called frustrated or non-collinear magnets. where there's some obstruction to the magnets just all aligning or anti-aligning, depending on whether you have ferromagnetism or anti-ferromagnetism. The simplest example is if you consider an antiferromagnet on a triangular lattice. So if you would like, for example, take the first top spin to be up, point up, you might want to think that the ground state there should be like its neighbor should point downwards, but then you see that the third guy can't be in the opposite direction of both its neighbors. And so some more complicated structure arises. These magnets have been studied experimentally, but the experimentalists don't agree on whether this phase transition that occurs in these magnets is second order or first order. And the ones that claim that it's second order, they find different critical exponents and also RG scaling relations that should be obeyed if it's a second order phase transition are not obeyed often in these critical exponents. So how can the conformal bootstrap help here? How can it resolve this? Well, if there is a second order phase transition, then it would be described by an O2 cross O2 or O3 cross O2 CFT. And it's a very simple question to ask, do these CFTs exist? Conformal bootstrap can help us do this, answer this question. So CFTs come with something called an operator product expansion, which takes a product of two operators in a correlation function and replaces it with a sum over single operators. You can keep doing this in your correlation functions to in the end reduce everything to two-point function. And by this way, everything can be expressed in terms of this coefficient by which the operators are weighted. Moreover, there's multiple ways you can do this. If you take, for example, a 4-point function, you can take the OP between the first and second and the third and fourth operator, or you can also take it between the first and third and the second and fourth. This means that you get a consistency relation on these OP coefficients and the spectrum, which are the terms that are allowed to appear in this sum. And you can use this to, so the CFT is not consistent for just any choice of these values. And so you can do a numerical test to exclude a certain assumption on the spectrum. And the spectrum is equivalent to these critical exponents that you would like to determine. Since given the time, I will jump now immediately to the results. So we find that there's no ON, if you consider this wider class of ON cross O2 chiral CFTs, then there's no CFT for n smaller than 3.78. So specifically, there's no O2 cross O2 CFT or 3 cross O2 CFT that could describe this second order phase transition. And so we can conclude that there is no second order phase transition, and the phase transition in these frustrated magnets must be first order. This plot, which I guess I don't have time to fully explain, but it just tests the same information. It's nice in a talk to include some plot and not just some number. It shows how for different dimensions, the critical n below which the CFT no longer exists, what this is for different values of the space-time dimension. And specifically here at 3, we find this 3.78, which excludes. I also included some other theoretical predictions on this line. And specifically, we exclude this scenario that some people have put forward where this CFT would exist for all values of n. Because this red line is the bootstrap lower bound. So clearly excluding this scenario where there's this turnaround. Thank you.
Questions? Yes.
Why it has to be this kind of CFTs?
Right. So that's a more complicated question that would require more than the 4 minutes. So you can work out basically by looking at these ground states, you can work out what the order parameter should be, and you'll find that the order parameter that describes the fluctuations around at this phase transition would be in a bifundamental of ON cross O2 cross O2 or O3 cross O2, and here the number O2 or O3 depends, just like in Ising, or just if you have a normal magnet, if it's constrained to be up or down, you would get a Z2, and if it's free to move in the plane, you get an O2, and if it's free to move completely, you get an O3. This O2 or O3 depends just on whether the magnet is free to move in the plane or in the full space. So both those magnets in principle exist, but yeah, we show that neither is shows a second order phase transition.
But the zero temperature state, everyone agrees, is Néel state, like an ordered state in this system, say triangular.
So you have either this one or you have like one where these, so they are they make a 120-degree angle between.
Okay, thanks a lot. The next speaker is Brunner Scheichen-Hitchfeld from MIT.
Okay. Okay, so what do I want to tell you about today? I want to tell you today about Quarkonium transport and weakly and strongly coupled plasmas. So I don't expect you to right away understand what I mean when I say those words. So let's first decide what am I even talking about. So Quarkonium, on one hand, is a bound state of heavy quarks. So a CC bar pair we call J psi, a BB bar pair we call upsilon. They have well measured masses. And the other crucial part of the title of my talk is plasmas. Specifically, I care about QCD and its high temperature limit, where we have a quark-gluon plasma. And we want to understand what's happening up here, because the quark-gluon plasma is a state in which we have deconfined color matter. So we would like to know how to probe its properties and what questions we can ask about it. One question that we can ask is to put these bound states into the high temperature phase and ask what their dynamics is. So, well, let's do that. What's the first thing you'll get out of this? So assuming that the quarks are heavy, they'll be sitting together quite closely. The plasma will not be able to see the distance between them because it's at a temperature lower than the heavy quark mass. And what it will do to leading order in a parameter expansion that I will not specify here because that would take too long, is to make these heavy quark pairs transition between color singlet and color octet states. In the same way that you can make a hydrogen atom switch, transition between different energy levels by hitting it with light. In practice, what you have to calculate that encodes the information of this physical process is a chromoelectric field correlator with an adjoint Wilson line in between. The physics is that you had a singlet state at the beginning, then an electric field kick from the medium generates a transition to a color octet state, then you have a propagation with an adjoint Wilson line, and then you go back to a singlet state. Okay, so if you want to calculate this, you can do several things. The first thing you do is do a perturbative calculation in QCD. This is it. I'm not going to explain it. It's just a lot of diagrams. But the quark-gluon plasma that we care about is actually not very weakly coupled. It's quite strongly coupled. And motivated by successes using holography to describe the quark-gluon plasma, we'll do exactly that. Now, what can we calculate in holography that's relevant for this phenomenology? Well, the thing we learned earlier this week is that we can calculate Wilson loops quite well. And we do that by essentially finding the extremal surface that hangs from a boundary contour that hangs into ADS5. How do these Wilson loops help? Because I told you I wanted a chromoelectric field correlator. They help because you can insert field strengths along the Wilson line path by taking small derivatives with respect to the boundary path, which you can formulate as well in the holographic side. You can just calculate the extremal surface with small deformations around the given boundary contour and take derivatives here. And you can then evaluate that Wilson loop. So pictorially, what you have is that you have an extremal surface, you introduce small deformations, you solve for the equations of motion into the bulk, you take that solution, replace it back onto your action, you get the on-shell action, and you can then take derivatives and calculate the correlator of interest. So in the final seconds I have, I'll tell you what we ended up doing for the background Wilson loop. And to describe that adjoint Wilson line, we found that it was really crucial to preserve this property from the QCD Wilson line, which is that you can decompose an adjoint Wilson line in terms of a fundamental and an anti-fundamental line, which are the inverse of each other. And to preserve this property in holography, if we keep the S5 coordinate explicit, we found that the right thing to do was to flip the S5 direction as you go back through the loop. And that's all I can tell you in 5 minutes. If you want to know more, you can have a look at the papers, or better yet, let's chat right now. Thank you.
Okay, I assume these large Wilson loops are not calculated in QCD?
No, no, we're doing it in N equals 4 CBM mills because that's the first thing to do, basically.
What's the next?
The next thing to do right away is to see how good of an approximation is that for the actual quark-gluon plasma, and then see if you actually need to calculate more QCD-like things to capture the dynamics of in-medium quarkonium. And what we're doing right now is actually using the results we got for this correlator and trying to extract some numbers out of it and see if we can describe data with that.
All right, let's thank Bruno again. Okay, the next speaker is Javier Subils from Nordita.
Okay, so by now we are already convinced that holography is a powerful tool to probe, to understand strongly coupled gauge theories. Let me remind you that the starting point for this was a stack of ND3 branes at the tip of a cone over S5. And then we learned from Igor that if you want to introduce some interesting dynamics like confinement in this picture, you are instructed to change the compact manifold by some more involved space. And in this way, you can get confinement. The reason being that when you go and compute the quark-antiquark potential, because in this system, the geometry is capping off smoothly at the infrared, the string has nowhere to go. So at some point, it has to lie at the bottom of the geometry. And the quark-antiquark potential is given by the length of this string. And because, crucially, the strings cannot break, because here you don't have any branes or black holes where the strings can be attached, you get a linear growth of the quark-antiquark potential, and thus you claim that this theory is confined. The system we're interested in studying was a similar one. So the starting point was a system with D2 branes, thus we will be describing a three-dimensional theory. And we consider these D2 branes at the tip of a cone over a complex three-dimensional projective space. And it gets a similar system as in the conifold is realized. So you have this S2 fiber over S4, and you can arrange the system in type 2A supergravity such that the S2 rings, and you also get confinement in this system. Interestingly, if you turn on the F2 flux in type 2A, what happens is that, well, first of all, this introduces Chern-Simons interactions in the gauge theory side, and you destroy the infrared. You find that there's some curvature singularity, but fortunately you can regularize it by looking how the solution looks like in 11 dimensions. And here's something that we didn't expect happen, which is that if you go now and try to compute this Wilson loop in 11 dimensions, well, first of all, what you have to do is now you have one more dimension. So you have to compute the area of a membrane, which is wrapping this extra dimension that you have incorporated, which is called the M-theory circle. And in this particular solution, what you see is that the M-theory circle also rings. So you get that the isolated quark, which is these two strings that were hanging, now it's allowed to break. Now, I mean, this configuration is allowed because since you are losing the boundary at the infrared, the string can split. So if you go and compute the quark-antiquark potential here, what you see is that the Wilson loop fulfills a perimeter law instead of an area law. So you had this, when this was not present, you had this confining regime, but then when you introduce these Simons interactions, what you get is that the quarks are screened by, by the Chern-Simons interactions, and the Wilson loop, you get a Higgs phase somehow. So in this system, one thing you can ask is this proposal that we have been talking about at some point of whether you can probe confinement with entanglement entropy. So in this particular situation, we see that if now we compute the entanglement entropy of a strip and it's complementary, in both cases, we get that the entanglement entropy as a function of the width of the strip has a phase transition for some critical width So in this particular case, it's not able to differentiate between the confining phase, where there were no Chern-Simons interactions, and the Higgs phase, where we had turned on the Chern-Simons interaction. So in this case, this wouldn't be a proper order parameter, if you want, for confinement. So, okay, this was a starting point. I summarized in 4 minutes the last 7 days of my life, well, part of them. So, okay, this leads to some other studies in this same system, but especially I want to, there was a lot of people involved, thanks to which this was possible. So here are the names. Thank you.
Thanks a lot. So is the infrared theory?
Juan had a question.
Yeah.
Okay.
Is it basically n=1 supersymmetric SUN Mills? Can you say
so at the UV, it's some SUN cross SUN plus M. Yes, n=1 supersymmetry. Yeah.
Far in the IR, can you say
well, there is this cascade that we didn't examine at all, but yeah, that's something we are still thinking about.
Okay. There was a question, right?
Yeah, so we talked about an 11-dimensional solution. Is that solution regular?
Yeah, yes, that I should have emphasized that. So the 11 solution is completely regular. At the infrared, the curvatures are completely finite. Yeah.
Okay, great. Let's thank Javier again. And the next speaker is Charles Tao from Uppsala University.
Okay, so I'll talk about the Hagedorn temperature of ABJM and how we compute it from integrability. This is work together with Simon Irkhammer and my supervisor, Joe Minahan. The Hagedorn temperature is defined as just the lowest temperature at which the thermal partition function diverges. And yeah, the theory we computed it for is this ABJM theory, which is the 3D n=6 superconformal Chern-Simons theory based on the UN level K cross UN level -K gauge group. And this theory is integrable in the limit where we take n to infinity, but we can keep the TÜV coupling n/k fixed. And then it's dual to string theory on ADS4 cross CB3. Now, looking in the literature for the Hagedorn temperature in ABJM, there's exactly 2 terms in the weak coupling expansion that are known. But with integrability, we can go much further. The technique we used is called the ABJM quantum spectral curve, which was developed first to compute anomalous dimensions of operators in ABJM, but it can also be quite easily adapted to compute the Hagedorn temperature by just changing some assumptions on asymptotics. And with this, we can compute so perturbatively, we can solve this this ABJM quantum spectral curve to 8th order in coupling. I'm not going to show the exact analytic expressions for these additional terms. I'm just going to show you the plots where I add consecutively higher order corrections. Now, this perturbative expansion has a problem. It's diverging. So its radius of convergence is somewhere here on this plot. So that's not quite nice. It gets a little bit better if we use a Pardee approximation to this recoupling expansion. But the good trick to go much further is to solve the quantum spectral curve numerically. And so once we start our numerics, we can let Mathematica run for a couple of weeks, and then we can get a plot like this, where I plot against lambda to the 1/4, and we get out to like 2.7, which is quite strong coupling, and we can actually fit a strong coupling expansion to this numerical data. And then we can start asking the question, does this match against the ADS4 string theory? And well, the slope, this asymptotes to, and also the constant term, they match exactly with what we find in the literature. But we can go further. From an effective perspective, we computed 2 additional terms to this expansion. And this lambda to the minus a half term, it matches exactly with what we find from the numerics. Now, in our effective approach, this shift in the 0-point energy of the string is not determined, so this term is not completely determined, but we can determine what this delta C is from our numerics, and we find that it's compatible with this -3 log 2 value, and this is consistent with also what the computations we did in ADS5 CFD4, and it has since also been checked by these authors. And let me finish by showing you what other computations have so far been done from the quantum spectral curve for ADS-CFD. And yes, so thanks.
Thanks a lot. Questions?
Yes.
Could you say a few words of how the corrections were computed in the sigma model side?
I am not, I think, the expert on this with one of the. So we had an effective, yes. So the effective theory, basically, oh yeah, sorry. You mean from the effective approach. So basically what we did is, so in the string theory side, one can also look at the string that runs around the thermal cycle. And we basically, one can describe this in terms of a scalar field in a supergravity background, and ask when does the string should be when does the string become massless, and the equations for that to get these additional terms, it turns out it's just doing some perturbation theory for a d-dimension for in this case 3-dimensional harmonic oscillator, and yes, that's what we did.
So the 3 comes from sum over 0.10.
This 3 here. Yeah, I think that one comes from just literally that we're in the 3-dimensional harmonic oscillator that gives you this 3. Yes. Yeah, so all these coefficients here, one can also write them in terms of d and then adapt it to different dimensions.
Thanks a lot. Okay, the next speaker, Shahrazad Zareh from NYU.
Hi, so in these 4 minutes, I will try to summarize part of our ongoing work with Sergei Dubovsky and other collaborators on the effective field theory of rotating strings. Previously, we studied a weakly coupled string description of SUN Yang mills, which models the glue balls as rotating folded closed strings. And this description showed agreement with the spectrum of 3D glue balls. But to go to higher dimensions, to calculate higher order corrections, and to maybe the energy splittings, and basically to find an effective theory for these rotating strings, we needed to study the endpoints more carefully. So we started with an open string that I'm going to focus in this talk. So imagine we have an open string with large spin. We can write this classical background, which recovers a rigid trajectory, but it also gives us a metric which becomes singular at the endpoints. And the singularities cause the higher order derivative terms in the bulk action to become singular, and the derivative expansion to break down at some point. So what we did was to vary the effective thickness of the endpoints, and by doing that, we're able to calculate the higher order the corrections due to these higher order bulk operators, and also the boundary action, which carries the information of the boundary conditions. And well, basically, we saw that those ambiguities of these higher order bulk operators are actually encoded in the boundary action or boundary terms. So up to subleading order, this boundary action has two independent Wilson coefficients. We calculated the corrections to the spectrum due to this boundary action. So these are the up to subleading order corrections to the spectrum. And the first terms are just j to the power of 1/4 correction to the Regge trajectory. On the other hand, we also calculated the corrections to the spectrum due to higher order bulk terms. And we got the same structure, except for a shift in the coefficients, which suggests that these higher order bulk contributions could be thought of as renormalized boundary Wilson coefficients. We also calculated the energy excitations, radial and transform fluctuations, and saw the same story to be true for the Dotto-Regge trajectories. So these are the corrections due to the boundary terms, but the higher order terms, higher order bulk terms give the same corrections except for a shift in these coefficients. At the beginning, I mentioned that our motivation was to study glue balls. So next step would be to study closed string, where we expect the same approach to be useful. Thank you.
Thanks a lot. Question.
So these coefficients M1, M2 that come from the bulk come from which bulk term? The fourth power of the curve?
Yes. So like I didn't write the bulk action just to, because I didn't have time to show that. But yes, so they come from like K4 term. Okay. Yes.
Okay, let's thank Shahzad again. Okay, Zechon Zhang from École Normale, Paris.
This study is about bootstrap the lattice Yang-Mills theory with my supervisor Volodya Kazakov. So thanks to the previous lectures and talks, I think I don't need to explain what lattice gauge theory and bootstrap is. So I just clarify that this is in the large N limit and in with 2D, 3D, and 4D space-time dimension. And we are working with conventional Wilson action. There is no fermion. So I will just show a simplest case. I will work out to set up what the bootstrap condition is in this situation. So the first step is the so-called Marcinko-McDowell loop equation. That is basically the Schwinger-Dyson equation for this lattice Yang-Mills theory with Wilson action. So you are doing a infinitesimal shift on some link, and you get some exact relation between the expectation of Wilson loops. Let's take an example. That is a 2D case, 2D lattice Yang-Mills. So you're doing the shift on the link of one plaquette, and you get the following loop equation. This is the exact loop equation. And there is some other kind of loop equations that's called the backtrack loop equation. You are doing the shift on the backtrack, and you get some other relations among different Wilson loops. This Wilson loops, this kind of category of loop equation, it is independent of the to-Hooft coupling. The second step is positivity condition. The positivity condition comes from a rather transparent observation that the Hermitian conjugation of matrix times the matrix itself, then you take the trace, it must be positive. But this becomes non-trivial if you consider the linear combinations of the Wilson lines. So in this case, we consider the Wilson line, the two Wilson paths bending around the single plaquette, and their linear combination C must be positive. It means that this matrix, it is positive semi-definite. The result of it is rather trivial, that UP is smaller than 1. But if you consider different starting point and end point, and the different linear combinations of Wilson lines linking the 2 points, then the result can be rather non-trivial. For example, we consider the Wilson line start at 0 and end at 0. So this is a length truncation for Wilson lines. So you will get some length truncation 8 positivity. This matrix is positive semi-definite. It is a 9 times 9 matrix. And this matrix contains 6 independent Wilson loops. These are all the Wilson loops with length cutoff 8. And we have already shown that it satisfies this McInkle-McDowell loop equations. These are actually all the conditions. Yes. So after setting up the optimization condition, we can maximize or minimize the 1 plaquette average. When we set lambda equals to 1, there is an upper bound and lower bound. Lower bound is trivial. And the exact value here in 2D, we have the exact value 1/2. And then let's push it up to 4D and push up the length cutoff to 16. This is the final result. And when we are increasing the cutoff from 8, 12 to 16, we get the yellow region, orange region, and the blue region. The purple and the red point in the middle, they are the Monte Carlo result. We see that for the physically increasing weak coupling region, the bootstrap upper bound is very close to the Monte Carlo result. Okay, thanks.
Questions? Yes, please.
Do you have an intuition as to why the upper bound is really close to the Monte Carlo answer, the weak coupling, and then lower bound is really close to the strong coupling?
Yes, there is some heuristic argument to justify it, because in this case, your action is plaquette average, or you want to minimize the action. So what you want to, your action is minus the plaquette average. So when you want to minimize the action, so you want to maximize the plaquette, so it is close to the upper bound. But when the lambda, it is big, the plaquette is suppressed, you are dominated by some entropy, then the upper bound and lower bound, they are almost equally close to the exact value.
Okay, let's thank John again. Last talk this afternoon, Xianglong Lu from Brown University.
Hello, everyone. So today I will talk about Largen optimizations for multi-metric systems, which is based on part of this paper written with my advisor and collaborators. So let us start from this very simple and basic 2-matrix quantum mechanical problem with M1 and M2 are 2 n by n Hermitian matrices. And this Hamiltonian is UN invariant, and the singlets, which we also call loops, are simply the traces of matrix products. And here are some very simple examples, and there are infinitely many of them. And in Largen limit, we can actually express the original matrix Hamiltonian in terms of a collective Hamiltonian, which is a loop, which is in terms of this loop variables phi of C, and their canonical conjugate as PC. The important part is that you can see that in Largen limit, the potential term actually dominates. So a Largen background is given by the minimum of this collective potential. But in the same time, the matrix omega appearing here is actually positive semi-definite. And one can show that it is equivalent to the Cauchy-Schwarz inequalities. And in this matrix problems, the collective potential usually is unbounded from below, and the minimum is located at the point where the constraints get saturated. So the constraints actually matters in this problem. And the simplest way to satisfy these constraints is to use master fields, namely the matrix elements. So in the end, we are led to minimize this collective potential in loop space, but the loops are computed by the matrix elements. So let us turn off the couplings of two matrices so that we have two copies of one matrix problem. And one can show that the results agrees very well from the weak coupling to strong coupling. So these are large background state energy. And furthermore, we can also do one expansions for these problems. And here eta and p are simply the small fluctuations of the loop variables and their canonical conjugates. And one can show that all orders in one expansion can be generated from our collective Hamiltonian. Here, e.g. S0 is order n squared, is a large background state energy, and H collective quadratic is order 1 and is a quadratic term. So the spectrum of these small fluctuations is simply given by the square root of the eigenvalues of this matrix. So before we move on to the two matrix problem, let me show you some simple examples for one matrix quantum mechanical problems. In this case, we have an analytical results which shows epsilon n equals n times epsilon 1. And one can see from the left figure that the numerical results show this relation for various Corti couplings G4. And on the right figure, I present epsilon 1 versus different couplings. And one can see that they agree very well with the analytical results. Now let us move on the two matrix problem. In particular, one can see that in the free case, we have these degeneracy patterns. Okay, so as we turn on interactions, these degeneracies are lifted. So one can conclude that at very large energy levels, this degeneracy is totally lifted, and we actually have a continuous spectrum in very high levels. So I will stop here. Thank you.
Have you tried this at negative G4?
Yes. So here in the one matrix model, on the left figure, you can see that we tried the negative G4, and we have a critical coupling. I think it's -1/3 square root 2, something like that.
It still works similarly when the two are coupled?
Oh, yes.
Question. Time for one more question.
Could you say a few words of the method you use? You mentioned you use the master field. Is that time independent or?
Oh, it is not time dependent. So, we just use n variables to parameterize M1 and n squared variables to parameterize M2, and we just use this to compute the trace to give the loop variables, and we plug into the collective potential to minimize.
Direction?
Sorry, what?
I'll ask privately.
Okay, well, I want to thank all the speakers for preparing such excellent talks and keeping to the time, and Emily for keeping the time. So.